Let's talk about, well, everything. The stuff that makes up the entire universe. From the phone in your hand to the farthest star, it's all connected. So let's jump right into this explainer on the nuts and bolts of the world around us. Seriously, just for a second, look around the room. You see your desk, maybe a cup of coffee, the window. It all looks totally different, right? But what if I told you it's all made of the same fundamental stuff? And that stuff is called matter. The definition is so simple, but it's incredibly powerful. For anything to be considered matter, it just has to do two things. It has to have mass, and it has to take up space. That's it. If it meets those two criteria, boom, it's matter.
So let's break those two rules down. On the left, you see mass. That's just a fancy way of saying how much stuff is packed into an object. On the right, you've got volume, which is how much space all that stuff fills. You know, a bowling ball and a beach ball might take up the same amount of space. They could have the same volume, but you know for a fact the bowling ball has way more stuff or mass packed inside it.
So what is this stuff, really? Well, if you could zoom in, and I mean way in, smaller than anything you could imagine, you'd find atoms. These are the tiny, fundamental building blocks of, well, everything. All matter is just a collection of these incredible little particles. Okay, so now that we know what matter is, how do we tell different types apart? I mean, gold and plastic are both matter, but they're obviously not the same. Well, we tell them apart by looking at their properties, their unique characteristics. First up, you've got physical properties. These are the things you can notice or measure without actually destroying or changing the substance itself. Think about it. You can measure the color of a car, or its weight, or its length, and it's still a car, right? Same thing with boiling water. It turns into steam, but chemically, it's still just water. That boiling point is a physical property. But then you have chemical properties, and this is a whole different ballgame. A chemical property doesn't describe what a substance is, it describes its potential to become something else entirely. For example, a piece of paper's flammability, its ability to burn, is a chemical property. It describes its potential to react and turn into ash and smoke. And this slide leaves it out perfectly. Physical properties, on the left, describe the substance as it is, right now. Chemical properties, on the right, describe how it might react to become something new. The big question to ask yourself is this. To observe this property, do I have to change the fundamental identity of the stuff? If the answer is no, it's physical. If it's yes, it's chemical. So these properties aren't just sitting there. They directly relate to how matter changes, which naturally brings us to our next section. Let's look at what happens when matter is in action. And guess what? It follows the exact same logic. In a physical change, the stuff is still the same stuff at the end of the day. You tear paper, it's just smaller pieces of paper. You melt an ice cube, it's just liquid water. But a chemical change, that's when a new substance gets made. You burn a log, and you're left with ash and smoke. That is definitely not wood anymore. That's a chemical reaction. Now, here's a really cool and fundamental idea. Whether a change is physical or chemical, one thing is always involved: energy. It's either being absorbed, like energy from a stove melting ice, or it's being released, like the heat and light from a burning log. And according to the law of conservation of energy, that energy is never actually created or destroyed. It just gets moved around. Speaking of reactions, I've got a question for you. What's a chemical change that you see pretty much every single day? Maybe it's something you do in the kitchen. I'm really curious what you all come up with. Drop your answer in the comments below. All right, moving on. Let's talk about the different forms or moods that matter can be in. You definitely know these. We call them the states of matter, and it's all about how those tiny little atoms are behaving. So in a solid, picture all those particles packed together super tight, basically locked in place, just vibrating. That's why a solid holds its shape. Now add some energy, like heat. The particles start to break free and slide past one another. Now you've got a liquid, which takes the shape of whatever container it's in. Adding in more energy, and those particles start flying around like crazy, really far apart. And boom, you've got a gas, which will expand to fill any space you give it. But wait, there's a fourth one. At crazy high temperatures, you can get plasma. This is where it gets so hot that atoms actually start losing their electrons. We don't see it much here on Earth, aside from lightning, but get this. It's the most common state of matter in the whole universe. It's what stars are made of. And just to tie this back to what we learned earlier, changing state is a classic example of a physical change. When ice melts to water or water boils into steam, its form is different, but its chemical identity is still H2O. Nothing new was created.
Okay, so we've got all this matter in all these different states with all these different properties. It's a lot. So how do scientists keep it all organized? Well, they have a pretty slick classification system.
And it all starts by asking one very simple, very direct question about whatever sample of matter you have. Can you separate it into different parts using a physical change? If the answer to that question is no, then you're looking at a pure substance. Think of pure sugar or pure copper. It's made of only one thing. But if the answer is yes, then you've got a mixture, like salt water. You can just boil the water away, a physical change, and you're left with the salt. You've separated it.
Okay, so let's say we know we have a mixture. We can drill down one level deeper. The next question to ask is, does it look the same all the way through? Is it totally uniform?
If the answer is yes, it's what we call a homogeneous mixture or a solution. The parts are so perfectly blended you can't see them, like when you dissolve sugar in your tea. But if the answer is no, it's a heterogeneous mixture. You can clearly see the different bits and pieces, like the different colored minerals in a chunk of granite, or, the best example, all the toppings on a pizza. Phew, okay, let's do a quick recap. The big takeaways are, matter is anything with mass and volume. We describe it using physical or chemical properties, which are linked to physical or chemical changes. It hangs out in 4 main states: solid, liquid, gas, and plasma. And finally, we can classify any sample of it as either a pure substance or a mixture.
And that's pretty much the grand tour of matter and its properties. If you found this helpful, it would be awesome if you could hit that like button, share it with someone you know, and definitely subscribe so you don't miss what's coming next. Okay, I'll leave you with a little puzzle. Using everything we just went over, how would you classify the air you're breathing right now? Think about it. Is it a pure substance or a mixture? And if it's a mixture, which kind is it? Let that one sink in. Thanks so much for watching.